Let's review the stoichiometry island diagram. This is the basic structure, the basic tool for the mind whenever we're doing stoichiometry. On the left, we have the substance whose quantity we know. That's these four islands: mole island, which is the triangle right here, and then on the left, mass in grams, volume in liters or cubic decimeters, and then particles here on the bottom, atoms or molecules. On the right, we have a mirror image of those four islands, and these four islands represent the substance whose quantity we are asked to calculate. To get from one island to the next, we have to cross these various bridges. Each bridge represents a conversion factor in a calculation, and I recommend that you memorize these bridges one to the next. For example, right here in the middle of the island diagram, you need to use the coefficients in the balanced equation when you're crossing this bridge. The upper bridges, molar mass in the upper left and molar mass in the upper right. Below those, 1 mole is equal to 22.4 liters or 22.4 cubic decimeters. That is only for gases at standard temperature and pressure. And then the islands at the bottom, 1 mole is equal to Avogadro's number of particles. We're going to use this diagram repeatedly throughout our studies of stoichiometry. At STP, how many molecules of oxygen react with 632 cubic decimeters of butane, which has the chemical formula C4H10. So if we use our stoichiometry island diagram model, since we're asked to calculate a quantity of oxygen, we know that the four islands on the right represent oxygen. On the other hand, we're given the initial volume of butane, which means that the four islands on the left represent the substance butane. Since we're starting at volume of butane, we're going to start on the left in this middle island, and we're going to go to moles of butane, and then we're going to cross the middle bridge to moles of oxygen, and then we're asked to calculate particles of oxygen, that is molecules, so we're going to go down and to the right. So when we do a stoichiometry calculation, we always start with the quantity we're given. We know from our tool for the mind that we're going to need 3 conversion factors because we're crossing 3 bridges. Let's go ahead and fill those conversion factors in. The first conversion factor has 2 quantities in it: 1 mole of butane and 22.4 cubic decimeters of butane. We know that the 22.4 cubic decimeters of butane have to go in the denominator so that those units will cancel. Now we need to cross the middle bridge, and to do that we need a balanced equation. So we have to step aside and write a balanced equation. Oxygen, as you know, is diatomic, so it has the chemical formula O2. So our reactants are butane and oxygen. We should recognize that whenever a hydrocarbon, butane is 1, whenever a hydrocarbon reacts with oxygen, we're going to get 2 very predictable products: carbon dioxide and water vapor. So now we need to balance this equation. I'm seeing 4 carbons on the left side, so I'm going to put a 4 in front of the CO2 on the right side. For now, I'm just going to put a 1 in front of the butane. I'm also seeing on the left 10 hydrogen atoms, so over here on the far right, I'm going to put a 5. 5 times 2 is 10 hydrogens. Now let's count up oxygens on the right side of the equation. 4 times 2 is 8, plus another 5. That's 13. 13, unfortunately, is an odd number, and there is no whole number that we can put in the blank next to this oxygen to make that happen. So this ratio, 1 to 4 to 5, that's a good ratio. It's just too small. So I'm going to double that ratio. Change that 1 to a 2, change the 4 to an 8, change the 5 to a 10. Now let's count up oxygens on the right side again. 8 times 2 is 16, plus 10, that's 26, which means we can put a 13 right there. Now we have a balanced equation, and we are now able to cross this middle bridge by looking at the coefficient ratio between butane and oxygen. And there it is, 13 moles of oxygen for every 2 moles of butane. Notice that we've put the moles of butane in the denominator so that they will cancel like that. Then the last thing we need to do is convert moles of oxygen to molecules of oxygen. And we're going to use Avogadro's number to do that, and type that in and get 1.10 times 10 to the 26th molecules of oxygen. If the question had been how many atoms of oxygen react with 632 cubic decimeters of butane, we would say, well, since we have 1.10 times 10 to the 26 molecules of oxygen, that is, molecules of O2, and in every 1 molecule of O2 there are 2 atoms of oxygen, our answer would have been 2.20 times 10 to the 26th atoms of O. Notice that we have the same number of significant figures in our answer as what we started with. 632 has 3 sig figs, and our answers also have 3.